All right, so we're going to continue with Unit 8 here, and this is really going to be a lot of review because we really, in essence, have used the Pythagorean theorem a lot with a lot of things that we've done this year, but we're specifically going to use it to find side lengths in triangles let me just shuffle these real quick here, in Unit 8, Lesson 2, here on page 94, and you can see that this is standard 8.2. I can use Pythagorean theorem to find missing sides of a triangle. All right, we're going to skip the opener and just go right down to the Pythagorean theorem here. Right? And we know that the Pythagorean theorem is a squared plus b squared equals c squared. And this works for right triangles only. Now, the important piece about the Pythagorean theorem is that c always has to be the hypotenuse. It always has to be the side opposite the right angle. All right, and I typically think of a as the horizontal leg and b as the vertical leg. And you can see that they're switched here in this picture, and that's okay. But it doesn't really matter, all right? But it's just a squared plus b squared equals c squared. Now, once again, we're going to leave our answers in exact form. So that means we're going to simplify our radicals just like we did in the prior lesson, and we're going to leave it like that. So we don't want any decimal answers. All right, so just real quick, when we look at problem 1 here, right? So when I look at this, I want to find x here. So I would say x squared plus 4 squared equals 6 squared. So then if I just go through my process here, right, so x squared plus 16 equals 36, and then that means x squared equals to 20. And then now when we're solving, I'm going to take the square root of both sides here. Now, typically when we solve, we would get a positive root and a negative root. Now, because we're working with a triangle, we're finding a side length, we assume we're only working with, all right, the positive root. All right, now that's a little bit different than just solving a regular equation. So we're only going to get the one answer here because we can only have a positive side length. Now, once again, when we look at square root of 20, all right, this goes back to our prior lesson. Can I reduce that number? And once again, I'm looking for a perfect square that is a factor of 20. And in this case, that would be 4 times 5. All right, and the square root of 4 is 2. And then I have the square root of 5 like that. And so there's my answer. So you can see that this is what we want to leave our answer like. That's an exact answer, and that's exactly what we want. Now I'm going to skip problem 2, and I'm going to go to problem 3 here. And just to show you how sometimes when we're looking for side measurements, we may have to use some information and draw in, all right, sides and things to make it a little bit easier to see. So notice when I look at this, I want to know this side right here, but I don't necessarily have a right triangle right now. But I can create one by drawing in this perpendicular line right here. All right. So I can draw that in, and this line that I drew in, it may not look like it, but it is parallel to this side right here. And it would also be the same length because it's the perpendicular to the same line. So that would mean that this would be 6. Now notice this entire length here is 10. Now once again, this length and this length would be the same. So that means that this piece would be 3, meaning that this piece here would have to be 7, so that the entire thing is 10. So sometimes I need to kind of go through the problem, draw in some segments, all right, think about the pieces in the whole, and then create a triangle. So now I have this right triangle where I can use the Pythagorean theorem to solve for x here. So this would simply be 6 squared plus 7 squared equals x squared, right? So 36 plus 49 equals x squared. So 70, so 85 equals x squared. And then I would take the square root of both sides. So square root of 85 would equal to x. And in this case, if I divide 85 by 5, I think I get 37. So 5 times 37. So I don't think we can reduce 85. So that is our final answer. All right, so you can see how that works. And when you flip to page 95, right, you have several examples here. Right, I want you to work through those. I'm going to wrap up with just one little bit of notes here on Pythagorean triples. Right now, what a Pythagorean triple is, these are sets of positive integers. All right. So that make a squared plus b squared equals c squared true. So basically, these are the side lengths of right triangles. Okay, so an examples would be, all right, a 3, 4, 5 triangle. All right, a 5, 12, 13 triangle. Okay, now what's really cool is once I find one set of Pythagorean triples, we can multiply by a scale factor and create similar triangles right? And so we know that from our prior unit in similarity. So once I know 3, 4, 5 works, I know 6, 8, 10 would be a Pythagorean triple. And I can multiply that by 3, and I know 9, 12, 15 would be a Pythagorean triple. All right, so once you find one Pythagorean triple, you really now have created an infinite amount of Pythagorean triples because I can just keep multiplying, right? So once I do that, all right, so a non-example, all right, would be like 3, 4, and 6, right? That's not going to be, and we just did, if I do that real quick, so 3 squared plus 4 squared does not equal to 6 squared, right? So that's 25 does not equal to 36. All right, so that is definitely not a Pythagorean triple. All right, now, however, what we're going to learn later, all right, is that we can, all right, use some of these relationships. So even though they're not Pythagorean triples, these will tell us information about certain types of triangles. So that wraps up a very quick lesson on Pythagorean theorem. So go ahead and finish all your problems in this lesson, and I will see you next time.